Hey students, welcome. This is 6.5. This is the ideal gas law. Remember, this goes on the right side of your page. So let's kind of just jump right on in here. So ideal gas law actually comes from the KMT or KMT, and this is our kinetic molecular theory. And what the kinetic molecular theory talks about is it talks about gas particles. All right, gas particles in motion. All right, so we're talking about them being in motion and moving around. And so it gives us four postulates from there, but this is where this ideal gas law is derived. So this is where it comes from, just so we're all on the same page. Now, the formula that we use there is PV equals nRT. And we've actually seen most of these variables before, with the exception of one. And the other one that we may not know is the one and we'll get to that in just a second. So our formula is PV equals nRT. P is pressure. And our pressure has to be in either atmospheres or kPa. All right, so we have to either be in kilopascals or we have to be in ATM. All right, and there's a reason for that, and we'll see that just below. V stands for our volume. All right. This has to be in liters. We have to be in liters to use this one. N is moles. So this is the one we've seen before, but we maybe didn't recognize with the N. All right. And remember, a lot of times with moles, we might have to go from grams first to moles, right? Or from grams to moles. So to go from grams to moles, how we do that is we divide by the molar mass. And vice versa, if we need to go from moles to grams, like at the end, we would multiply by molar mass. And we'll see an example or two where we get to review that. R is the completely new one, the one we haven't seen at all, and that is our gas constant. Okay, capital R is our gas constant, and we have two choices, and they go back to our pressure above. So if we have our pressure in ATM, we're going to use 0.0821. Whereas if our pressure's in kPa, we're going to use 8.314. So those are our two choices. This 0.0821 is on the back of our periodic table, so that might be the one you use. Just convert all your pressures to ATM. And last but not least, we have our temperature. T is temperature, and we must have it in Kelvin. So let's kind of go ahead and work a little example here and see if we can't figure this out from here. Remember our formula, is PV equals nRT. And let's read through this. We have a sample of hydrogen gas with a volume of 8.56. That's volume. We have a temperature of 0 degrees C. There's my T. Pressure of 1.5 atm, so that's P, and we're supposed to calculate the number of moles of H2. So writing out here to the side, we have P is 1.5 atm, we have V, 8.56 liters, all right, N is our moles, that's what we're looking for initially. We have R, which is our gas constant. And since we have ATM right here, we're going to use 0.0821 because our pressure, right, 0.0821. T is our temp. That's got to be in Kelvin. We're currently at Celsius, so we're going to add 273.15 to that, obviously giving us 273.15. So let's go ahead and plug it in and see what we get. So we've got 1.5 times 8.56 is equal to N times 0.0821. Times our temp, 273.15. Okay, now we're ready to go ahead and solve. And as I've been walking around, I've been seeing you guys, you got to go ahead and do the multiplication. So we've got 1.5 times 8.56. And that one comes out to be 12.84. And then N times, and we're going to take 0.0821 times 273.15. And we're going to get 22.43. All right, now we need to isolate N, so we're going to divide 22.43 on each side to get N by itself. And N is going to be coming out to 0.57, 0.57. And that's our first question, 0.57 moles of H2. That was the first part of the question. Now this next part of the question says, then find number of grams. We've got to go from moles to grams. And if we look up here, we said to go from moles to grams, we could multiply by the molar mass. So we're going to put that as a little aside over here. We've got H2. We know 2 times 1.00794 H. That's going to give us 2.02. All right, that's our molar mass. 2.02 grams per mole. And if we use our little T-chart, we've got 0.57 from over here, moles of H2. And we know 1 mole of H2 has a molar mass of 2.02 grams. Boop, boop, moles cancel. And so we're just going to take 0.57 times 2.02, and this is going to give us our grams. We're going to get 1.16, and that's grams of H2. Awesome. Okay, sweet. Let's look at that next problem, and we're actually going to change something on this next problem. It'll make you really happy, I'm sure. So here we go. We've got a weather balloon containing 1.10 times 10 to the 5th moles. That's what we're going to change. We're going to change moles right here to grams of helium. It has a volume of 2.70 times 10 to the 6th liters, 1 atmosphere pressure, and we're calculating the temp. So P, V, N, R, and T. Okay. Our pressure go through 1 atm. This time we do have our volume. We've got a big volume. This is actually, if we take it out of scientific notation, we're talking about 2,700,000 liters, which makes sense that it would be a big volume because we're talking about liters, all right? Or we're talking about a weather balloon, and that's obviously going to be a big deal. Now, if we look here, I'm going to erase this R and T for just a second, because what we have is 1.10 times 10 to the 5th grams of helium, but that's not moles, and we need it to be moles. So going back up to the top, to get from grams to moles, we need to divide by the molar mass. So this is where we go to our periodic table, and we're going to divide by 4.003 grams of He and 1 mole on top of He. This will get us to moles, which is what we're going to look for. So we're going to take 1.1 and then e to the 5th times, divided by 4.003. And that's going to give us 27,479. If I've done my math right, 0.39. And that's moles of He. All right, then we've got our gas constant R. Since we're at ATMs, we're going to use 0.0821. And then our temp is going to be what we're looking for, our question mark. So kind of plugging this in down here, PV equals nRT. We know our P is 1. We know our volume is that giant number, 2,700,000, is equal to N, 27,479.39. I got a little messy there. Let me try that again. All right. Times our gas constant, 0.0821. And times our temp, which is what we're looking for, T. All right. So multiply each side. Obviously, this side is going to be 2,700,000. And this side, we're going to take that 27,479.39 times 0.0821. That's going to give us 2256.06, and that's T. So if we divide each side by 2256.06, 2256.06, beep, beep. All right. 22,700 or 2,700,000. Man, Griffith's having trouble with words right now. 2256.06. Our temperature in Kelvin will be 1,196.78. Woo, Kelvin. That's a warm one. 1,100 Kelvin. The other part of this question says it wants us to go to degrees C. So to get from Kelvin to degrees C, here's our formula. K equals degrees C plus 273.15. So 1196.78 equals degrees C plus 273.15. If we subtract 273.15 on each side, we will get our Kelvin or our Celsius temperature. Man, that was rough. We should just start that again there. All right, so if we subtract 273.15 from each side, we will get our Celsius temperature, 923.63 degrees Celsius. Still warm. All right, see you next time.